In 1997, we inserted the telomerase gene into normal human skin cells, grown in a petri dish. When we observed that the telomerase enzyme was being produced in these cells, we then assayed the telomere lengths. We noticed that the skin cells were essentially becoming immortal. There was virtually no limit to the number of times the cells could divide. When the lengths of the telomeres were assayed and we got the results in, we observed that the telomerase cells had actually lengthened their telomeres rather than seeing the telomeres get shorter. The critical question then was whether or not the cells were becoming younger. A few years later, another lab inserted the telomerase gene, the same gene we were using, that already had very short telomeres. These cells were then grown into the skin of the back of mice. Now, in this experiment, they had old mice, young mice, and telomerized mice. When looking at the old mice, we noticed that the skin was getting wrinkled. It blistered easily, and we noticed some gray hair. As for the young and telomerized mice, there was virtually no difference. When we looked at the gene expression patterns between the young and telomerized mice, we noticed that the genes being expressed were virtually identical between the two. This created very exciting possibilities for us because it was the first evidence showing that telomerase cells actually return to a young morphology. They look young, they express the same genes as young cells, and this is where the impact of telomerase on aging is truly going to have a lot of potential and excitement.